As promised, here's a work solution to the first exercise. This is from part 2 of the Inverse Function Theorem video. And what we've got is a situation where we've got f is a differentiable function. This is from Rn to Rm. In our context, eventually n equals m, but here it doesn't matter. And y is some fixed element of Rm. And we take the magnitude squared of y minus f of x. And we want to find out, the claim was that we could calculate the gradient. And in fact, negative of the gradient was of more interest to us. Okay, so this is a good workout with derivatives. You could do it entirely in terms of the gradient, but really I want to think about the matrix of derivatives. The derivative is a linear transformation. So the main thing is the chain, or one of the main things is the chain rule. The derivative of a composition is the composition of the derivatives. To be more precise, the derivative of the composition at, let's say, x is ds evaluated at t of x, composed with the derivative of t at x. And that's always important, that you have to evaluate at t of x, not at x. Okay, so what is going on here? Why do I invoke the chain rule? Let's say s of z is magnitude z squared, or a much better way to write that if you want to invoke algebra is z dot z. I like to emphasize this is geometry, this is algebra, and it's algebra that interacts better with formulas in calculus. And then t of x is the rest of it, y minus f of x. Okay, and so we want the derivative exactly of the composition, because this is really the composition of those two things. Okay, so excuse me. Let's first take the derivative of s. Actually, I'll probably put it somewhere else. So remember, this is the place where you evaluate it, but then this whole thing is a matrix, or really more fundamentally a linear transformation, so we need to plug in a v into it. And you could do that in terms of, just write it out in terms of like the component formula for the dot product, but it's so pretty and easy to do it by the definition, we might as well. We're just going to take the limit. We're just going to write out, let's see. What we're going to do is we're going to take z plus, just to get a sense of it real quick, z plus, let's say, tv. I'm going to start at z, and I'm going to walk in the direction of v, right? And I'm going to dot it with itself. We just really want to figure out what's the first order part of that. Okay, z dot z, that's the constant part. Okay, and in fact, we subtract that off to get the derivative. So this is really how you start thinking about derivatives in a very basic way. You start at your base point, and you add in some small multiple. We want to think of t as small. Eventually, we would take the limit as t goes to 0 of some vector. Okay, and then you get tv dot z plus z dot tv. That's 2t times z dot v, because of the symmetry. And then plus t squared v dot v. Okay, and then we're just going to divide by t. Okay. And then we're going to take the limit as t goes to 0. Okay. So what I'm really calculating is the directional derivative. And this guy goes away because it still has a t in it. This guy cancels, and you get 2z dot v. Okay. We can make that a little more official if you want, but the key thing here is the ds at z applied to v is 2z dot v. Hopefully a somewhat familiar result, because it shows up so much in derivatives and geometric applications of derivatives. Now dt of x applied to v, remember t was just y minus f of x. The y minus doesn't do anything, or the y doesn't do anything, and so you just get d minus df of x applied to v. Okay, so we just need to compose those, and we'll be done. So, might want to pause the video. Make sure you do that yourself. Okay, so we have ds composed with t at x applied to v the parentheses start to stack up here, but that's when you get to more advanced mathematics, that's what happens. It's not the deep part of it, but it is part of it is dealing with the parentheses pushing. Okay, so that's ds at x applied to dt at x applied to v. Alrighty. Oh, sorry, t of x. That was the whole thing. T of x. Okay, so ds at t of x, okay. So the t of x is going to go in here, or that's in other words y minus f of x. So it's 2 y minus f of x dotted with all this stuff, okay. But dt of x was just minus df of x, so minus df of x on v. Okay. So one thing is that I actually was not being careful with my signs. I forgot there were two minus signs coming out. The derivative here actually does have a minus sign, and then when we take minus the gradient, the minus sign will disappear. So minus 2 y minus f of x dotted, that's a vector dotted with another vector. What happens when we take v into the matrix df of x spits out another vector, and then we're going to dot it with this guy. Okay, so that's the derivative written out very explicitly, and this is of course hy. So that's the derivative matrix of hy applied to v. Now how do you get that as a in terms of the gradient? Well, let's just strip off the v here. They're both something applied to v. So dhy at x is just minus 2 y minus f of x. Okay, well, the dot product, we need to express that in terms of matrix multiplication. We want to see this all as just one big matrix acting on v. Well, here's one matrix acting on v. What's the dot product? Well, we replace that with a transpose of this guy, and then that becomes matrix multiplication. Okay, so there's the matrix. Now I've been able to strip off the v. This matrix, put a v over here, is exactly what this guy is, and that was the dot product we had before. Okay, and then the gradient, or minus the gradient, we just do two things. Obviously the minus sign is going to cancel out, and then the gradient is just this row vector. Let's just make sure we know the dimensions here. Okay, so like v here was in Rn. df of x, as I said in the other video, is an m by n matrix times a vector in Rn, gives you a column vector in Rm. This guy already was in Rm. It was a column vector. That makes it into a row vector, and you dot it, or you multiply, and you get a scalar as we want. Okay, so this guy is this row vector, a 1 by m matrix, times an m by n, and then, excuse me, that is a 1 by n matrix, a row vector, as befits the derivative of a map from Rn to R1, and then the gradient is just the transpose of that. So the minus signs cancel, and when you take the transpose, these guys, the order flips, and there you go. So both of these will actually show up, both in this form and in this form. It just really depends on how you like to see it. But it's a good workout with the mechanisms of derivatives, matrix of derivatives, and a little bit of linear algebra.